Okay, hello and welcome. I'm Travis McEwen, and this video we are going to be going over a little bit of networking, talking about IP addressing, how the scheme works, what a subnet mask is, and then a little bit into kind of talking about subnetting or the different sizes that relate to networking as a whole, and then also some of the more key component parts of network as well, such as what is the range of addresses do we typically use, what's a default gateway, and then also, if I have a little bit of time left towards the end of it, how a static route kind of works, and also how we can use ping, the ping protocol, to determine a little bit more about troubleshooting when we're working on a network. So let's go ahead and get started. So first thing that I'm going to do is we're just going to be using Excel just to kind of as a way to show the address as a whole. So we're going to look at, say, just a standard address that we've probably seen a little bit, which is 192.168, say, like 10.0. Now, then we're also going to add in what's known as our subnet mask. And typically, you'll see something like 255.255.255.0. So again, what we see right here is this is our, say, our network, and this is our subnet mask. So what we're looking at, and when we're reading an IP address, and when we're looking at kind of networks as a whole, networks are define the size of the actual LAN itself. So how many IP addresses actually exist, how many devices can exist within that single given LAN, and the size is determined based off of the subnet mask. Now, before we get too far into it, a quick little thing to note is that how we kind of read a subnet mask is if you see a 255, it means that the octet directly above it or related to it in the same octet is locked in place. It means that all of the bits that exist in that octet are turned to an on state. So essentially what this means is our first three octets here, or 192, or 168, and our 10 are all locked in place. However, this last one right here is free and available for us to kind of manipulate. It's open. So we have, in this case, a block of 255 that we can kind of play around with. Now, let's dive a little bit deeper into kind of what I meant by these are locked in place and that term octet. So in each of these, in an IPv4 address, it's broken into 4 sections separated by a period. Now, I don't have a period here just because we're using Excel, but there's a dot in between the 192 and 168, a dot in between the 168 and the 10, and another one in between the 10 and the 0. Now, each of these has a total of 8 bits that exist in each of these individual sections. And in each individual section, they are represented by a number chart of 128, 64, 32, 16, 8, 4, 2, and 1. And these are the numeric representation of the 8 bits. So it doesn't matter which octet we're looking at, these numbers are the exact same in the first, second, third, or fourth octet. Now, what these numbers are essentially telling us right here is that, again, if they're all turned on, so flip to an on state, then this is all locked in place. So it means that if we add these all up, it equals 255. Really 256, but that's because we'd be including, say, the 0 if we were counting from base 0, which we typically do. but this gives us our 255. So what do I mean by they're on? Well, remember, in binary, we have a 1 and we have a 0, where 1 we can equate to on. Oops, got this Excel. And 0 is equated to off. So if I see a 1 there, it means it's flipped on. If there's a 0 there, it's turned off. So in this case, when we're looking at this 192.168.10.0, or specifically just the 192 right here, and we see this 255, it means that all 8 of these bits have been flipped to an on state. So that means that all of these bits are locked in place, and I can't use anything that exists in that octet. So same thing for the 168, all bits are turned on, and same thing for the 10 octet, all bits are turned on. I can't use any bits in 83. Now this last one, it's a 0, which means that all of the 8 bits in the final octet are free and available for me to manipulate. So in total, I have a total of 255 IP addresses free and available for me to kind of manipulate. Again, really it's 256, but we'll get to that in just a little bit more. So when we look at this, how we kind of associate or read this a little bit, another way of reading a subnet mask is also by what's known as a CIDR, or also known as a slash notation. So another way of reading a CIDR, or a representation of 255.255.255.0, is to also call it a what's known as a slash 24. Now, how we get a 24 or a slash 24 is we're just stating that we're adding up all of the bits that are currently locked in place. Well, my first octet is all locked, so we add that 8. Second is all locked up, so we add that. That gives us 16. And the third octet is also all locked, so that gives us 24. So a slash 24 is another way, or a shorthand way, of saying 255.255.255.0. So that, hopefully that kind of explains a little bit of the different kind of terms of what a network, or kind of how we kind of read an IP address. Now, getting a little bit more into a network as a whole, a network is broken up into a couple different categories. We have what's known as the network address. We typically want to also define the first usable IP address. We would also want to try and define our last usable IP address. We would want to define what our mask is, so our subnet mask. We'd want to define our CIDR, or slash notation. And then I forgot one extra thing that we'd want to do as well. Besides last usable, we also want to define our broadcast address as well. And we'll talk about what a broadcast here is in just a sec. So to kind of go over, what we are talking about here is our network address is always the absolute starting point of a network. So it's almost always 0. Not 100% guaranteed, but in this case, for what we're doing for our representation here, our network is starting at 0. So it's the absolute starting point, the very, very first. Now, this is not a usable address. I can't assign .0 to a PC or an interface. It's not an address that can be given out to anything. So not a usable address. So our first usable is the actual first address that I can give out to an actual PC or a router or interface that exists. So in this case, what we want to do is add in our first usable is just that, it's just 1. So you just count up by 1. So it's, in this case, it's 10.1. That's the first usable IP address. Now, the next thing to kind of go really quickly is, before we talk about the last usable, we want to look at what the broadcast is. Now, remember, we have a total of 255 in our fourth octet. So what that tells us that we have 255 available IP addresses, kind of. So our range here can go from anywhere from 0 up to 255. If it goes over 255, well, then that would roll into the next network, and this would become 11.0. So in our case now, our broadcast is going to be 192.168.10.255. It's the absolute maximum, the last address in the actual network itself. Now, again, this isn't the last usable, because a broadcast address is a special type of address. This address is used by all devices within a given LAN or network. So any device can utilize this. Again, a broadcast message is kind of the catch-all address. It says, hey, I don't know where to go, or who I'm supposed to talk to, so I'm going to broadcast this message out to all devices within the LAN, and hopefully the person that I'm trying to talk to, or the PC that I'm trying to talk to, will hear it and respond back to me. So our last usable, this is the last IP address single IP address that I can hand out to a system, is 1 less than the actual broadcast itself. So in that case, it is 192.168.10.254. And so again, we've talked about our mask. In this case, it's 255.255.255.0, and our CIDR, as I've kind of talked about as well, just about here, is represented by that /24 is what we have. And then the last thing that we typically want to look at is number of usable hosts. So this is what we mean by this, is the actual number of IP addresses that I can hand out to all systems, and this goes from 1 to 254. So I have 254 available IP addresses I can hand out within this given LAN. So so that's the general gist of kind of what we have. Now, if we look at, say, setting up an actual network, something similar to what you might have done in another lab would be, let's just set up and draw out a brief network here. I'm not actually going to really configure anything, but that's okay. Well, maybe I will, but probably not. So in a network like this, let's say we had 192.168.10.0/24 as one network, 192.168.20.0/24 as another network, and our point-to-point link as 10.0.0.0/30. So again, we can see that it's like, okay, we know where our 24s are. Now that I've set a /30, well, if we a /30 really quickly, just to go over it, just means that we're counting up the bits that we're turning on, starting from the 24th bit. So we would say the 25th bit is turned on, the 26th bit is turned on, 27th, 28th, 29th, and 30th bits are turned on, with the last 2 bits still being free and available for me to manipulate. So that's all a /30 is really telling us. So if we wanted to look at that, another way of representing what my mask would be 255, 255, 255, and then adding all those bits up, it's 252. So my mask would be 255, 255, 255.252. So another couple things that we're going to label here is we're going to label what these addresses would be. So we'd say, I'm just making up a few addresses. I'm just shorthanding it. Overall. And what I mean by shorthanding is I'm just not writing out a couple of the octets. So for instance, on this PC, it's 192.168.10.50. I'm just representing it with a 10.50. Let's zoom in just a little bit to make that a little easier to see. And then same thing with, say, this gigabit 01 interface. I'm just representing it with a 10.1, but it is part of the short. I'm just shorthanding and leaving off the first 2 octets there of 192.168. So here's the important thing of kind of what we're talking about. In this topology has a total of 3 networks. We have one network represented in blue, another network represented in red here, and a final network, our little point-to-point link here, represented in green. Now, each of these networks, trying to move that a little bit, there we go. Sorry about that. Each of these are LANs or networks. That term is synonymous with each other. Local area network or network, tomato, they're synonymous between each other. So in this case, one of the important things that we're going to be talking about here is what is a default gateway and why do we need it? So if our PC here wants to leave this LAN, it needs a doorway out. It needs a gateway, a method of leaving the LAN. And that's what the default gateway is. So without a default gateway, without a doorway, this PC will only be able to communicate within this blue circle. So the furthest point it would be able to talk to is to that 10.1 address. But it wouldn't know to forward traffic towards 10.1 if it was destined for another location. For instance, if when PC 0 wants to send traffic out towards another device over to, say, like PC 1, it would build a frame. And now in this frame of what we'd actually see, we'd have our separated into, we'd have, say, a layer 2 header, a layer 3 header, and then we'd have our data section. Now this is a simplified version of what a frame would look like. Now remember, inside the layer 2 header, we have the source and destination MAC address. Inside the layer 3 header, we have the source and destination IP address. So when my network here is building an actual frame itself, So when my PC is actually building a frame, and let's say it wants to send traffic over to, say, PC1, how it would actually go about sending that traffic is we're going to ignore the, well, I'll go over a little bit of this. We'd have, let's add in our hypothetical MAC addresses as well. And I'm just going to represent it just as letters here, just to make it a little easier to kind of go over. So normally, again, remember a MAC address is 48 characters in length, all hexadecimal. I'm just going to be representing it shorthand with, say, AA, BB, CC, DD, E, and FF. So in this case, when our PC is sending a message over to PC1, PC0 is, it's going to build its layer 2 header and its layer 3 header in the frame. So it's going to first start by building the layer, adding on the layer 3 header. So it's going to go, okay, well, where am I sending traffic to? I'm sending it over to 20.15 is the destination, with the source being myself, or sorry, not 15, it's 50, 20.50, with the source being myself at 10.50. And then once it adds that information, it goes, okay, well, then I'm going to add the layer 2 MAC address. And remember, our layer 2 header, our MAC address information, only exists within the LAN. So what this device will do is it'll go, okay, well, I know my source, which is AA, but now I need to know, where do I forward this traffic? So it will look, so our PC is a layer 3 device. It will look at its routing table, look at its ARP table, and it will go, do I know where 20.50 is? Does that exist within my scope of information that I know? And it will go, no, I don't. But I'm told I need to get there. So what it will do is it will look at its information at its table, at its ARP table, and at its routing table, and it will go, okay, I don't know where to do it, but since it doesn't exist within my LAN of 10.0, I will send it to my default gateway, which is my doorway out of my LAN. And so in the destination MAC address, it will forward and mark that as where the traffic should be forwarded to. So that frame will have this information. It will have the destination MAC address will be BB of the actual frame itself. So our line here, as it goes up to the actual switch, so that frame is sent out to the switch will accept this frame. It will look at the destination MAC address. It'll go, okay, do I know where this is? I do. It's attached to my FAO2 port, so it forwards it up to out FAO2 towards this router. The router will then accept that frame and then will remove the layer 2 header so that it can read the destination IP address of 20.50 and check its routing table to make a forwarding decision from there. So the important factor there is that if PC0 didn't have its default gateway set of 10.1, when PC0 went to check, when it goes to check its routing table or its ARP table to figure out where to forward traffic to next, if that default gateway address didn't exist, then it would just drop the traffic right at PC0, and the traffic would never actually leave the PC. It would just immediately fail. So the default gateway is extremely important to allow this PC to leave it's LAN. So that's an important thing. All right. So that's about it for right now. I don't want to ramble on for too much longer. So I'll have more videos posted about talking about IP addressing, how data flows through a network, and we'll talk a little bit more in depth about this as well down the line. So, all right. Have a good one.